Hello guys, welcome to another tutorial session of the Applied Electricity course, IoT. So this time we are going to continue with our basic circuit analysis, IoT. And we are going to talk about the current division. You get it? Please try as much as possible to join the Telegram page, so that if you have any question, you can ask them. Okay. Maybe you watch my videos and you are struggling to understand certain things. So if you're able to join my Telegram page, you'll be able to ask any question that you want. Okay. I don't read the questions that are dropped at the comment section. I always focus on those on the Telegram page. So try as much as possible to join the Telegram page so that you can ask any question that you want to ask. And also, the videos, right, that links to what I'm doing right now is in the description. So try as much as possible to watch those videos so that you understand what we are doing here. If you've not watched any of my videos, please try to watch it. And don't forget to subscribe. Subscribe to my channel. You get it. And you click on the notification bell icon to get updates on all the videos that I upload on this page. So please try as much as possible to join the Telegram page as well. You get it. So to set the ball rolling, we are going to discuss the current division. So let me show you a simple circuit here. Right. We are talking about the current division. Current division. Okay. So let me draw a simple circuit. I can have a circuit, right, with a current source instead of a voltage source. We have a current source. Okay. Then we also have, let's say, a circuit which is what? Power to what? Or the resistor which is power to what? The source. Let me call it IT. And I call this one R1. Right. And we also have another resistor here. You get it? And we also have another resistor here. So let me call this R1, R2, and R3. Okay. Let me draw a fourth resistor so that I'll expose it to something. Let me add a resistor here. I'm going to expose it to something very important. Some of the mistakes that students used to do. So I'm going to expose it to it so that you don't find yourself in such situation. So let me call this R3, and let me call this one R4, right? Then I'll add another resistor here, which is R5. Okay. Yes. In circuits, right, there is a fact which I want to state over here. A clear fact. When two resistors, or when two or more resistors, or let me say when resistors are in parallel connection, right, what happens? The voltages are the same. Voltages are the same, but the currents different. Current values are different. Yes. So when resistors, right, are connected in parallel, like R1 and R2, you get it? The voltage across the resistors are the same, but the current values are different. I want to prove this to you with a software. Okay. Let me move straight to my software. That's circuit design. So this is a very simple circuit. Okay. Let me try to let me do it. Let me try to repeat the same circuit from that side. So I'm going to repeat the same circuit over here. So with this, I have one resistor here. Okay. have resistor 1 here. Very good. And I also have another resistor in here. Okay, that's fantastic. And between these resistors, let me put this resistor here. Okay, here it goes. So there's a resistor here and there's another resistor here. Very good. Let me reduce this resistor to, let's say, 260 ohms. I've reduced the value. Okay, sure. Then let me increase the voltage source to 24. I'm just picking a random value. Okay. As soon as I play this circuit, you see the current flowing through it. Okay. But we are going to use what multimeter and ammeter to measure the current flowing through what each resistor, as well as the voltage across each resistor. So let's move on to that side. Let me pick my virtual instruments. Just bring 2 of them on board. That's the voltage, the voltmeter and the ammeter. So I'm going to measure the current that is flowing through this resistor. So with that, I need to put my ammeter at this end. Do you get it? Yes. So I'm putting my ammeter at this end. Very good. Okay. Then I'll measure the voltage across that resistor. So let me measure the voltage across the resistor R1. Right. The same applies to this. Let me give it space so that it's clearer. Okay. So I have let me copy this. Okay. Then anyone who wants this software can alert me. Okay. If you want the software, if you are really interested in learning circuit connections, you need the software. So if you want the software, please alert me personally on my WhatsApp page. I'm going to drop my WhatsApp contact there. And if you want the software, let me know so that I'll give to you. Some people are really not interested in the software. So if you personally want it, let me know so that I can give it out. Or I'll show you how to download it. You get it, so that you will be using it even after your school or your course in applied electricity. So I have the voltage here. Let me also measure the voltage across this resistor. Okay. Yes. Then I'm going to measure the current and the voltage here too as well. So the current here, let me copy this. Move to this end. Okay. Drag it. This end, drag this one down. Now measure the voltage across it here. Okay. Look at the last one. So with the voltage here. Together with the currents. Okay. I want to expose you to something over here before we move on to our analysis. Right. Okay. We are good to go. Let's see what happens. Let me zoom in a little. Okay. Very good. Okay, let's see what happens here. So when I click on play, if you should analyze this very well, you can see that the voltage, right, across the R1 resistor is equal to what? The voltage across the R2 resistor, right? Because they are in parallel connection and there's no element between them. Do you get it? But the voltage across R2 resistor and the R3 resistor are not the same. This is because there's an R4 resistor, right, which has been connected between the R2 and the R3. So in that case, the voltage across the R2 resistor is not the same as what the voltage across the R3 resistor. But the voltage across the R3 and the R5 are the same. Why? Because they are in parallel connection. So if voltages are in parallel connection, their value are the same. Technically or ideally, right, you see that it's closer to what? 24. So at default, the voltage V1 should be equal to what? The R1 resistor, because they are in parallel connection. When the elements are in parallel connection, they also have the same. So in that case, the 24 and the R1 should be the same. Technically, this one should be 24. But because there are some losses, in the cable, that leads to the reduction in the voltage. So the cables here, there are some voltage drop. Practically, it shouldn't be so. Practically, there should be some voltage loss in the cable. But ideally, right, the R1 should also be what? 24 volts. So the voltage here and the voltage here, they are parallel. So they all have 24 volts. The same as the V1. But this one has a very different value. Has a very low voltage drop. Why? This is because the resistor here, right, is causing some voltage drop. And that makes this R3 to be what? To be unequal with the R2. Let me show you something. Let me copy this one and take off the, how do you call it? The R4. So let me duplicate this. Very good. Let me duplicate it. Then after duplicating it, I'm going to take off the R4 resistor. And let's see what happens. So let me go to the normal view and draw a connector around. So okay, very good. So let's see what happens. So you see that now with this one, when I took the resistor R4 off, we have the same voltage across all the resistors, because this this R6 resistor, R10 resistor, R7 and R9, they are all parallel. So because they are in parallel connection, their voltages are what? Are the same. But with this one, because it was having a voltage drop at the R4, the voltage R2 and R3 are different. So it proved to the fact that when two voltages or more resistors are in parallel, so when resistors are in parallel, the voltages are the same. Yes, it proved this point. Let me expand this. Okay, so voltages are the same when they are in parallel connection. You get it? So that is it. And they state that the current value out are different. So let's visit our circuit once again and see what's happening there. Okay, so the current value here is 72.63 milliamp. So you see this R1 and R2 resistor, they are parallel to each other. Okay. So when they are parallel, the current value are different, and that leads to what? The current division. Okay, that's what leads to the current division. So when resistors are in parallel connection, the voltages are the same, but the current on each path is different. So it leads towards the current division. So the current here is different, the current here is different, the current to the R3 is also different, right? And the current to the R4, R5 is also different. So let's look at the circuit down there. You can see that the R6 is having a different current value. The R10 is having a different current value. And the R7 is also having a different current value. The same applies to the R9. So when they are in parallel connection, they are different. Okay. Please, if you don't understand, just reverse the video and watch it again. And I believe that watching it multiple times will give you a better understanding. So let's move on. So because we've proven this fact, let's move on to prove our current division. That is our current division. Right. Let's prove our current division. What's the mathematical equation behind the current division? Okay. So let's move on. So if you take notes, I can get a voltage source here, right? This can be plus minus. You get it? But alongside, this one is producing a current, which is called IT. You get it? It doesn't matter whether it's a voltage source. So far as you know that this IT is producing, this voltage is producing a current, you are good to go. So it can be a current source, it can be a voltage source. Anything can happen. Okay. So let's move on. So I have a resistor here, right? I'm just going to use 2. Then after, I will expose you to certain things that you need to know. I've already exposed you to one of the things. That if, let's say, I have a resistor at this point, let me use a different color. If I have a resistor at this point, then it means that the voltage 1 is not equal to what? The voltage 2. Right? They are not equal. That is if I have a resistor there. But if there is no resistor here, if there is no resistor, okay, there is no resistor here, then they are in parallel connection. At that point, you can say that V1 equal to what? V2. Please take note of it. Students always make mistakes when it comes to something like this. They always think that so far as that resistors are there, right, they are having a parallel connection, but they are not. There's a voltage drop by a particular resistor. So take note of it. So it only holds when there is no resistor between them. But if there is a resistor between it, they are not in parallel connection. And that rule does not hold for it. Okay. So let's move on. So with this, right, I made it clear that at this point, the voltage are equal. V2 equal to what? V1. Do you get it? And at this point too, there's a current flowing through this path, which can be labeled as, let's say, I1. I already have I1 here. And there's a current also flowing through this path, which can be labeled as I2. That is, I also have R2 here. Do you get it? Yes. So with this one, from KCL, which we will talk about later on. KCL, right? With KCL, I can say that the current which is entering, right, is equal to the sum of currents leaving a particular node. When you watch our fundamental video, I made it clear to you that a node is formed when 3 elements, that's the principal node, right? Principal node is formed, right, when 3 elements comes together at a point. So you see, If you've not watched my first video, you are going to struggle to understand this. So please, try as much as possible to watch my first video. Are you okay? We've not talked about the KCL, but I'll upload a video on the KCL and KVL very soon. I decided to do this because it's more like an emergency. Everybody is wishing to understand the current division and the voltage division. That's the reason why I tackle the current division and the voltage division before tackling the KCL and KVL. So with the KCL, it states that at a particular node, right, the algebraic sum of current entering the node is equal to the algebraic sum of current leaving that particular node. That's the fundamental. Let me write it here. KCL states that at a node, right? Or let me state it this way. The KCL states that the algebraic sum of current at a node sum of currents at a node, right, is 0. Did this when you're in senior high school. Or we can say that at a node, the sum of currents entering is equal to what? The sum of currents leaving. That's the KCL, Kirchhoff current law. Do you get it? So if you look at this, the IT is what is entering the node. The IT is entering that particular node, IT here. And we have I1 leaving, right? And we also have I2 leaving the node. Do you get it? And because of this, right, we can state clearly that the KCL is giving us what? IT equal to what? I1 plus I2, right? That's the KCL. This one represents the second explanation, although they all mean the same. So the sum of current entering the node is equal to the sum of current leaving the node. Someone too can say that the algebraic sum of current at a node is 0. So the nodes leaving should be assigned negative, right? Whilst the node entering should be assigned positive. So in that case, I have IT, which is positive, minus the ones leaving, I2 minus I1, right, should be equal to 0. So the algebraic sum of current at a node should be 0. So in that case, if I should simplify, I'm going to get the same thing over here. That is IT equal to what? I2 plus I1. Okay. So the KCL is also very important here. I'm going to tackle a video on KCL and KVL alone. That will be the next upload. So let's move on. Let me redraw the circuit here again. This time with, let's say, a simple ink. Okay, so I have two resistors here. One here, another one too at this end. So I have my R1 here, and I have my R2 here. Then I also have the current flowing through this is called I1. And the current flowing here is I2, right? And I have the voltage here, V1, V2. Let me call the voltage here VT. There's a voltage at this point, which is called VT. And there's a current here, which is called IT. Do you get this? That's the reason why I was saying that this one can also represent, like, let's say, voltage. The source here can be a voltage source. So all of them, you need to be able to understand what you are doing. Okay, so with this, we've already made a clear view that when the resistors are in parallel, the voltages are the same. That is V1 equal to V2 and it's equal to Vt, right? So this Vt is parallel to the R1, is parallel to the R2. So they are the same. And we said that with KCL, we can state that the IT equal to what? This is the node. So the IT is entering. And the I1 and I2, they are leaving. So IT equal to what? I1 plus I2. IoT. So because of this, from equation 1, we can say that IT equal to what? I1 plus I2, right? But what's Ohm's law? Ohm's law makes it clear that V equal to what? IR. So assuming we are making I the subject, we are going to get I equal to what? V on R. So let's replace all the I's with the ratio of voltage to what? To resistors. So we can say that Vt on what? On RT, right, is equal to what? V1 on R1 plus V2 on what? On R2. We are good to go. Do you get it? But we know that V1 equal to what? V2 equal to V3. Sorry, Vt. This one. You get it? So we can replace it with, let's say, V. So let's replace that one. Because they are equal, we can replace it with the letter V. So I can say that V on what? On RT equal to what? V on what? On R1 plus V on what? On R2. Right? So on the left hand side of the equation, we can factorize V out. So let's factorize V out, and we are going to get V into bracket 1 on R1 plus 1 on what? R2. Do you get it? So if you should multiply both sides of the equation with what? 1 on, if you multiply both sides of the equation with 1 on V, we are multiplying this side with 1 on V, and we multiply this side with what? 1 on V, right? In that case, the V will cancel out the V. This V can cancel out the V here, and this V will cancel out the V. So what do we get? We are going to get 1 on what? On RT equal to what? 1 on R1 plus 1 on what? R2. And with this, please watch my first video. I simplified this one, and once you watch it, you understand very well. So we can say that RT should be equal to what? R1, R2, all on what? On R1 plus R2, right? That is RT. Please, I'm pleading with you. I pointed out some mistakes that students have been doing when, let's say, they are finding the total resistance. And I believe that all those who have watched that video have understood very well. Most of the time, in the previous years, I used to teach them in class. When I'm teaching them, then they will be realizing that this was the mistake they used to do, this was the mistake they used to do. And I believe that most of you here have watched it and know that, yeah, if you had not watched this video, you would have made that mistake. But lo and behold, you've watched the video and you've corrected the mistake. So those who have not watched my first video, try as much as possible to do what? To watch it and understand the errors students do when it comes to finding the total resistance when the resistors are in parallel. Okay, now we've been able to prove this one, the IoT. Let me redraw the circuit here again. Right. And I have my VT here, I have my IT here, and I have my R1 here. Right. then R2 here, R2. With R1, I have V1, I have V2, and I have I1 and I2. We've been able to prove that RT should be equal to what? R1, R2, all on what? R1 plus R2. Okay, very good. So assuming we want to find the current that is flowing through the R1 resistor. Okay, assuming we want to find the current that is flowing through the R1 resistor, then we can say that V1 equal to what? I1 R1 from Ohm's law. So with this one, we can clearly state that I1 equal to what? V1 on R1. But we know that V1 equal to what? Vt. So it means we can replace V1 with Vt. So we can say that I1 equal to what? Vt on what? On R1. But from Ohm's law, we know that Vt equal to what? RT IT. Right. So in that case, what do we get? I1 should be equal to what? RT IT. All on what? On R1. Okay. So, if we simplify this, what do we get? We are going to get, let's substitute the RT, the value for RT. Or let me even break this one. I have RT times what? 1 on R1 times IT. Right. Then let me substitute the RT there. Let me substitute the value of RT. Do the equation. Then I'm going to get R1, R2, all on what? R1 plus R2 times what? 1 on R1 times 1 times IT. You get it? Yes. So what happens here? We know that the R1 cancels the R1. So in that case, what do we get? We are going to get our I1 to be what? To be R2 on R1 plus R2 times what? The IT. And this is the formula for current division. That is giving us, let me write it here. The I1, that's the current that is flowing through the R1 resistor, can be giving us the what? The opposite resistance. The value of the opposite resistance, which is R2, all on what? The sum of the two resistors. That is R1 plus R2. All multiplied by what? By the total current, which is IT. Do you get it? Yes, so assuming you want to find I2, so you can pause and write I2. It's always the opposite resistor. The opposite resistor is always the numerator. So you can pause and write the current division for R2. For I2, the value is going to be the opposite resistance, which is R1, RAK, multiplied by the sum of the resistors, R1 plus R2, right? All multiplied by the total current, which is IT. Do you get it? Yes, very good. So, it's good enough. I'm going to use some few minutes to point out the mistake that students have been doing. Okay. Yes. So that is the formula for current division. So in that case, what if there are 3? When the resistors are 3, assuming I have a current value here. Okay, but before then, let me solve a simple question. Okay. let me solve a simple question. Let's say I have 8 ohms here, right? And let me use a multiple of 15, multiple of 3, sorry. I have, let's say, let me use 15 ohms here. Then I have 9 ohms here. Then this current gives me, let's say, 30 amps. And they've asked me to find I1, or the I1 here, right? I1. How do I find it? So basically, I can say that I1 equal to, at this point, you can choose to label the resistors. That is, let me call this one R1 and R2. So I1 is giving us what? The opposite resistance, that is R2, all on the sum of the resistors, that is R1 plus R2, multiplied by what? The total current, which is equal to what? IT, right? So in that case, I will say that the I1 should be equal to what? Should be equal to R2 is 15, all on what? 15 plus 9, right? Multiplied by the 30 amps, right? So what do I get? I1 should be equal to what? 15 on 824, very good. 24 times what? Times 30. Right? Yes. So if I should simplify, this 6 can go here, and 6 will go here 4 times. Then what do you have here? 6 will go into the 30 how many times? 5 times. So at the end, I'm going to get I1 to be what? To be 5, remember 1, 5 times 5 is 25, remember 2, right? And 5 times 1 is 5 plus 2, which is going to give us 75 on what? On 4 amps, if you simplify. Okay. Assuming I have IA here, and I'm asked to find IA. If you know the current value over here, it's very simple. You can just use, and you know the 30 amps, you can just use KCL, right? But assuming you don't know the current value at I1, then you can still apply the current division. That is, for IA, right? I will say that it is the opposite resistance, that is R1, divided by the sum of the two resistors, R1 plus R2, right? All multiplied by what? By the IT. And that gives R1 to be 9, all on what? 15 plus 9 times 30, right? And this will give us 9 on what? On 24 times 5 times 30. Sorry. So this gives 4, and it goes here 5. So at the end, you are going to get 45 on 4 amps. Are you okay? So that's a simple question under the current division. A simple question. We can get a complicated circuit where we need to apply the current division. But take notes. You see, most students, when they get the circuit, right, like they have about 3 resistors. 3 resistors here. Right. 3 resistors here. And I have R1, R2, and R3, right? And I'm asked to find, let's say, the current I1. You get it? Students apply current division. And with this current division, they focus on only these two resistors. If you do that, you are wrong. Please, I beg you. The total current here, IT, is being distributed to all the three resistors, R1, R2, and R3. So if you apply current division for only these two resistors, this is what the student do. For instance, with this one, I'm asked to find I1. And the student will be found writing this formula. I1 equal to the opposite resistor, R2, all on what? On R1 plus R2, all multiplied by what? Let's say the IT. If you do this, you are wrong. This is different from a circuit with only two resistors. See, the total current here is being distributed to all the three resistors. So you cannot just choose these two and ignore the three. So before we can find the current in the I1, we need to what? Reduce the circuits. That is applying circuit reduction. So I can reduce the circuits to this form, IT. Then I have my resistor here. That is what? The R1, right? Then I combine this circuit as one. That is the R2, 3, right? I combine it as one, which will give me what? R2, R3, all on what? R2 plus R3. That is the, let me wipe the bracket before someone tells me that the R2, R3 is multiplying what's in the bracket. So, something like this, the R2, R3 is equal to this. Okay, before you can apply the current division to find I1. So, you need to first reduce the circuit to this form. And after you've reduced the circuit, then you can find I1. Because this resistor is contributing to the total currents. So, I cannot just take it off and find the current division for only these two resistors. Especially, they always do that when they find a resistor here. When they see a resistor here, because we've made it in our lesson that these two resistors are in parallel and they are sharing the current. Then they will just ignore this part of the circuit and find the total resistance within this. Some people too, they don't focus in the middle, right? But when they ask them to find the total resistance, right? Then there will be a resistor here. Let's say there's a resistor here, right? Then they are going to use these two. They always use these two and they compare it to the IT, which is wrong. It's 100% wrong. So, assuming I'm asked to find I3, right? Some people will move on to say that I3 equal to what? The R2 all on what? R2 plus R3 times IT. It is 100% wrong. Let me use a red ink. Let me use a red ink to say a big wrong. It doesn't hold. It's a big wrong. IT. Before you can find the I3 here, you need to find the total current that is flowing to both the R2 and the R3. You don't use the IT. The IT is supplying current to the R1, the R2, the R3, and also any resistor here, let's say R4. You get this? Before you can use the total current, you need to know the current at this path. Because this current is the one that is supplying current to these two resistors. So you cannot just conclude that the current over here is equal to the current IT. Do you get it? Please take note of this. It's very serious. Okay. So in that case, if I want to find the current I3, it is rather the I3 equal to what? The opposite resistance, R2 all divided by the sum R2 plus R3 multiplied by I. So you first need to find the I before you do it. Students make this error. Students used to make this error a lot. So we don't just conclude by saying that this 2 is multiplying the IT. Please take note. So if I want to find it, like I said, I can reduce the circuit phase, right, so that it will be 2. And now to find I1, I can say that I1 equal to what? The opposite resistance, which is R2, R3, all on what? R2 plus R3, all divided by the sum, that is R1 plus R2, R3, all on what? R2 plus R3, all multiplied by what? By the IT. You get it? Yes. So please take notes. Reduce this one first and use the 2. So let's take another one. So for instance, let me draw the same circuit here. Let me draw the same circuit. I have a current source here, right? And I have my IT here. Then I have 3 resistors. One here, 1, 2 at this point. Then another one at this point. And this time, I'm asked to find, how do you call it? I2. You get it? I have my R2 here, R3 here, and R1 here. I'm asked to find I2. Take notes. Because there is no resistor at this point, there is no resistor there. So because there is no resistor there, I can change the position of the R3 to be something like this. If there is a resistor there, please, you can't. So it will be something like this. I'm going to change the position of the R3. So I have my R3 at this point. So the R3 can come here. Then it will be followed by what? Let's say the R2. So I can change the position. Because there is no resistor, I can change them easily. Do you get it? Yes. So I have my I2 here, R3 here, and the R1 here. Now that I've gotten this, I can combine these 2 resistors as one. So R1 3 can be given as, that's R1 3 can be given as what? R1 R3 all on what? R1 plus R3. So the new circuit will become something like this. I have my current here. Then I have a big resistor which I've combined, right? And the value are right here, R13 will equal to what? R1, R3, all on what? R1 plus R3. Then I'll get my I2 here. That is R2. Right. Once I'm able to do all this, then I can say that I2 should be equal to what? Should be equal to the opposite resistance, which is R13, all on what? The sum of the resistors. R13 plus R2, right? All multiplied by what? The IT. Do you get it? Yes. So that is it. Please take notes. There is a way, there's a very big formula. If, let's say, I have the 3, there's a very big formula. If, let's say, I want to, someone can say that, oh, what if I want to combine all the 3? Right? There is a way to combine all the 3. If you want to combine all the 3, right? I don't want to show you so that you go and what? And make a mistake when you are memorizing it. You see, I told you that I've had some experience in what? In circuit analysis. So if I get 3, I don't need to pass through what I've shown to you, right? I can just write the formula easily. So for instance, I have R1, R2, R3, right? And I'm going to find the current that is flowing through I1. So with that one, I can see that I1 equal to what? Equal to the product of the 3 resistors, which are R1, R3, right? The opposite resistors, the product of them, divided by what? The permutation, that is R1, R2, plus R2, R3, plus R1, R3, right? All multiplied by what? IT. This is because, you see, when I was showing you my first video, I told you that if you have 2 resistors in parallel and I find the total resistance, it's different from finding the total resistance of 3 resistors in parallel. So please, if you want to understand this concept very well, you need to watch my first video. Okay. So this one helps us to get I1. You can prove it. But you see, nobody is going to ask you to prove, let's see, the formula for current division and voltage division. You just need to understand it. So if you are struggling using this, please stick to the 2s, the 2 resistors at the time. And if you watch my previous video, I've explained all these things. So if you don't understand, just reverse the video again and you understand very well. At this note, we are going to call it a day till we meet again. Our next lesson, we are going to talk about the KCL and KVL. That's the last 2 basic circuit analysis that we'll talk about. So basic circuit analysis 2. Circuit analysis 2. Right. We'll talk about that one. But please try to subscribe to my channel. Right. Do subscribe to the channel and click on the notification bell icon, right, to receive any information that I share. You get it? So once you talk about the KVL, KCL, you are good to go. You can jump into complicated circuits, all the circuits that you're talking about, the Thevenin, the Norton, and all those circuits. So please try as much as possible to subscribe to my channel. Please subscribe to the channel and join the Telegram page. Join the Telegram page. If you are struggling to join, send me a WhatsApp message. Send me a WhatsApp message if you are struggling to join, and I will always respond to you. Okay, so on this note, I believe you are enjoying school very well. Yeah, on this note, have a wonderful day. All the best.